So, first part was just what are like terms. Now we need to make sure that we are very, very clear with what a like term is and isn't, and we need to consider all of the options which things could be like terms. All right. So, like I said, a couple of you, I think, well, you know, did you get it? Did you not? I think some of you are like you've said this is a like term and you're correct, and then you've said this is a not like term. It's like, well, no, you're wrong. So there's still something there. All right. So we've just, from our previous work, I remember saying to you yesterday, a term is a part of an expression that's separated by an add or subtract. So if you remember that investigation we did before about whether it was a monomial, binomial, that kind of thing, that should tell you what a term is. So we've got here some terms, two separate terms, and you are told they are like and those are not like. All right. So the question is, like terms are. How would we define like terms, Julian?
Like terms are when the ending, not the number, is the same. Okay. So like 3x and 6x, that's a like term because they both have x's at the end.
Okay. Yeah, go for it.
I would have needed to expand on this, but I said like terms are terms that have an element of sameness and an element of difference that are shown in the same spot. So like how...
Okay, so the reason why I didn't like that, and a couple of people said that, so have an element of sameness, alright? The reason why I couldn't accept that in the same spot, does this one in the not like term have an element of sameness in the same spot? Yeah, what is it? I've got an n there, and I've got an n there, which is an element of sameness in the same spot. I'm not chewing gum.
No, because they have to
Get rid
have...
of it if you are. But now you're trying to explain further, which hopefully you can see why I can give you that. So that explanation of the same thing in the same spot doesn't work all the time, right? So I would say this one, look, has a W, has a W, has a W, sameness, same spot. So that statement doesn't work, right? Okay. Anyone want to expand, Nate?
It doesn't follow the same rules like T and W together on that one, T and W together on that one. But when you go to T to T and the power of 2, and then W, it ruins it because it's not following the same rules as the other two.
And what's the rule you're talking about?
That the T is the T and the W that are supposed to be together, and then the power, and then there's not a power.
Oh, okay, right. So you, I was about to say, yeah. The T and the W are together in all three options, but what is true, like you've just added, is in this case the W is to the power of 2, and the T is to the power of 2 in that one. So that actually makes them different. And I might be able to give you a reason why it is going to be different. Go for it.
I just wanted to say that the number doesn't have to be the same. It only has to be the letters, for example, and I just wanted to ask, what's the difference between uppercase M and lowercase m?
They're different.
Are they just different numbers altogether?
Yes.
Oh, all right.
So in algebra, all right. Someone asked me this in the M1, I think. What was it, you guys? M1 test, algebra and angles. If a letter, right, is used more than once, so that's an X, that's an X, that X will be the same number. We can't write X and X to represent two different numbers. Does that make sense? So in algebra, what we end up doing, and this is how I would explain to you what a like term is, in algebra, what we end up doing is substituting the letter for a number once I know what the number is, yeah? So that means, as in substituting in sport, I replace the letter with the number represents. So, for instance, let's have a look at 2x squared y and 7x squared y. All right, so 7x squared y, 2x squared y. Now, if I say to you that x is 2 and y equals 3, right, what then happens? Well, this becomes 7 times 2 squared times 3, and this becomes 2 times 2 squared times 3. Now, 2 squared times 3 is? Well, 2 squared is 4, so 4 times 3, and this would be 2 times 4 times 3. So we end up with 7 times 12 and 2 times 12. Now, if you look at it, it now makes sense that that and that are the same thing. And they always will be. That's why they're like terms. So can you see why these ones would not be like terms now? Because once I replace them with numbers, they end up being different values, right? So a t, right? Again, so if we look at, right, what's it going to be? 3tw squared, and then let's just look at negative 2t squared w, right? Let's say that t equals 5, w equals 6. So this would be 3 times 5 times 6 squared, and this would be negative 2 times 5 squared times 6. So that would be 3 times 5 times 36, and this would be negative 2 times 25 times 6. So that would be 3 times negative 2 times. Will these two things give you the same thing? No. Could you work that out for me? You've got calculators. What would that be? You really need it. You're going to get rid of your gum as well on the way out. You're missing the instructions, by the way, aren't you? That's the thing. So be quick. Got calculators? Yeah, get it out. Come on. What is it?
540 for the top one.
540. Well, don't do the negative 2, just the 25 times 6.
Oh, wait, it's
150.
yeah, I did the
Oh, okay.
150.
Don't do the times by 3 then. What is 5 times 36? 180.
5 times 36.
5 times 36, yeah.
180.
180, yeah. Okay, so now look, this is actually 180, but this is 150. So they're not going to be the same number when I put numbers in to replace the letters, okay? So that's why they're not like terms. So one thing people get confused with algebra, it's like, oh, but it's all letters, what do I do? Well, actually, those letters are just going to become numbers. So the people that did well and wrote down it's the right ending, okay? We could explain that a little bit better, couldn't we? But I was generous. I was like, okay, that makes sense. If we ignore the number and we take the letters, do you remember what I said the letters were called? Begins with V.
Oh, variable.
Variables, good. I remember. So if the variable part is exactly the same, so I think like Nate said, it's the same pattern, it's including the powers and the letters are the same, then we have a like term. The number, which I think most of you got, which is the number doesn't affect it, right? There was one that came up though, which a couple of people didn't spot, which is negative 13 and negative 10 are like terms, but they have no letters. But isn't that still the pattern? There is no letters, right? If a letter is called a variable, do you know why it's called a variable?
Because it could be controlled, like controlled and not controlled.
Well, kind of. I would say what we can do is we can change the number that we put in for the letter. Like I said, we can have that control. So the letter can be changed. So another word for change is vary. Yeah, it can be variable. I'm allowed to change it, which is what. This negative 10. Am I ever going to get anything that's not negative 10? No. So what is something called if you can't change it? It begins with C.
Control.
Constant. Right. So that would be a constant. So this would be a variable term, this would be a constant term. So both of these are constant. So why are these not like?
Because one has a variable and one's a constant.
Exactly. This is the constant. This has got a letter which is a variable, right? So we've got lots of stuff. Now, I think, Nate, you picked a good one in yours. You picked one like this where look, I've got g squared and p cubed, and this is also g. They were good ones to look at and go, oh, right, okay. So this one, all the letters follow the patterns with the exponents, whereas this one doesn't, yeah? All right. So, in your examples, how could anyone have got upper grade above a 6? Because no one got above a 6. Really, it's because your examples, so I said for you, Nate, yours, both of the examples were exactly the same, just with different letters. All right? So you can see in the table, all right, there are lots of different options. We've got ones that are different letters, sorry, there's different numbers, positives and negatives. So if you wanted a better grade, up to a 7, for instance, in your examples, I would have liked to have seen different versions, things that were not quite the same. Yeah? Make sense? Okay. So part 2, collecting like terms. So this is the important bit. This is where we've got to take this knowledge going forward. So I hope everyone's on it mentally. Yeah? Okay. So some of you are not making any notes in your paper either, just to add to it, but adding your knowledge. I should need to say it 3 times. Alright. So how do we collect like terms to simplify?
Well, first you have to verify if it's a like term, and if it is, what you do is you do the operation represented in the equation. So for example, we'll do this off one because it's the easiest to understand.
Yeah.
3 minus 6. You would actually do that 3 minus 6, which would then equal -3, and then of course you have to add the x. The only question I have is, does that x also get affected by the operation, or does it stay the same?
Okay. The way that we want to start understanding this is a like term. I'm going to say this, and you might at first go, no, that doesn't make sense. I'm going to tell you that this 3, Andrew, is not a 3. No, I'm not trying to be overly. This is, well, the reason why I say it's not a 3 is because it's not a constant term. If it was a 3 on its own, it's a 3. But this is not a 3 because this whole term, do you remember I said we'll eventually have to put a number in for x, won't we? So if x is 2, what will that become? Won't be 32. It's 6.
Times 2.
This means here 3 times whatever x is. All right. What's the English words for times? We say 3 lots of. Yeah. So 3 multiply 3 lots of x. Bondi, pay attention. You especially writing these things down. So this, I always say, is not a 3. It's how many x's I have. So I have 3 x's, but I need to subtract 6 x's from it. So as Rory said, we just do the 3 take away the 6 because that tells me how many x's I have. We have -3 x's, yeah? Why do I need like terms?
So you can figure out the answer.
Well, why can't I do it with non-like terms?
Because then it would be like the same.
It's not the same. And
So for instance, if I say x equals 2, it would be 3 times 2 minus 6 times 2. So I would know that, well, instead of doing both of those things, how many 2's will I end up with? I'll end up with minus 3 twos, yeah? So I can just simplify it. But if, for instance, I had a 6 and a y, if I change that to a y, and I said y is 5, and I change that and say 6 times 5, does it make sense now just to stick them together? I've got 3 2s and I've got 6 5s. It doesn't make sense, does it? In my head, I'm just like, doesn't make sense to simplify it. I have to do those two things separately. So that's why it's important that we only do this with like terms. Yes?
I was really confused with the third one down in the expression.
Yeah?
Because they did 2x minus 5x, but 13 plus 10 on the simplified.
No, they didn't do 13 plus 10. They did negative 13 minus 10. Holden, I think, did this one very well in his example. He put boxes round, which is what I do, put boxes round the sign and the number, and he lined these, so I can rewrite it. I think a couple of people said you can just rewrite them together, and we do, well, it's 2 x's minus 5 x's, and it's minus 13 minus another 10. So 2 x's minus 5 x's is minus 3 x's, and minus 13 minus another 10 is minus 23, right? So I think, Nate, in your examples that were very, I think that's the, if you look over the page in your examples, that's what your negatives were the problem. Yeah? All right, so if we want to do one of these long ones, look, the first thing I would say when we're collecting like terms, like you said, we need to identify the like terms first. So, what's the same as g squared p cubed?
5g squared.
And I take the symbol in front of it as well, g squared p cubed. Any others?
Yes.
Plus another g squared p cubed. All right? So those three are the same. So I'm going to rewrite that as negative 2g squared p cubed plus 5g squared p cubed plus another g squared p cubed. All right. Is there anything that is the same as plus 8pq squared? H?
Minus 10p.
Yeah. Any others? No, that's it. So we've got plus 8pq pq squared minus 10p. Is that g or q? Oh, q.
The G.
I think it's more of a q. It's a weird q. But anyways. I put g's here and then I've gone into q's. That's why. I've just confused things completely, haven't I? That's it should be g's and p's. I'm going g's and p's. So it's the other way round, but I've got p and g squared, and I've got p and g squared. They swapped them round even, haven't they? All right, and then 5, like the last ones. So we've got a plus pg minus 6pg, and then just a constant. Good use of vocabulary. So we've got plus pg at minus 6pg. Now, what we do is then we can deal with all of those. So now we've grouped them. So I've got all of these together. So now, and this is how we can really explain, now I can kind of ignore the variables and just look at, well, it's negative 2, plus 5, and plus 1. One of them. So negative 2 plus 5 is positive 3 plus another 1. So we've got positive 4 g squared p cubed. Then the next one was that one. So now I look at plus 8 and negative 10 of them. So I've got
-2.
minus 2pg squared. Then it's this one, which is plus 1 and minus 6. So that's negative 5pg. And then we had the minus 6 that we should not ignore, the minus 6 on the end. And that is my simplified version. So I would just rewrite it as 4g squared p cubed minus 2pg squared minus 5pg minus 6. Right? And that's it. So generally, I think people kind of understood that on the whole. Right? There's a couple of things. But how you explain that? Well, I guess one thing for you to notice is look at all the space I gave you and how much of it did you use. You know, so if you want a better grade, it's about, yeah.
At the time, I was just worried about the time.
You had loads of time.
So I was just speeding through everything.
You had loads of time. All right. Now the final question. The final question for, well, actually, we did some examples. Again, if your examples were a bit samey, that's going to cost you. If you got examples wrong, yes?
You said I need to use variables, but I had an X there.
So look. Variables being simplified.
Oh.
You haven't, you've just got 4x, it's still 4x. Yeah. So I would like to see you have a 4x and a 2x that became 6x, for instance. Yeah. All right, the final question, I think 1 or 2 people got it right. Is it always possible to simplify an expression by collecting like terms?
I got this one. I said, I don't think it is always possible because there might not always be like terms in an expression. It just makes it easier.
So I don't like the it makes it easier. That we can discard the makes it easier because it's not any more difficult to do it or not do it, right? In fact, if there are no like terms, it's the easiest because we can't do anything, right? And that's the answer to this question. It's to get you to think, is it always possible to simplify? No. Because if there are no like terms at all, it can't be simplified. So that's an important. Can you all write that down if you haven't written that down in your final question? All right. Now, why is that response important? Well, I often see people that are given questions, and the question will be simplified where possible, and they try and simplify all the time, and then they get ones wrong because they think it can always be done. Right? And we can give examples, you know, so if we're justifying for criterion B, you know, we'll say no because, well, 2x plus 4x plus 8g plus 10g will simplify to 6x plus 18g, okay? So that is simplified, but 3x plus 2y minus 10g plus 15a, can that be simplified? Cannot be simplified. Why can't it be simplified? It does not have any like terms, yeah? No like terms. So in an assessment, I can now, for instance, quite happily give you one, and your answer, if I say simplify this, your response should be it cannot be simplified. Now that's not a trick question, that's a question that tests your understanding. Alright, so that's very, very important. Alright, any other questions on this? All good? Do we understand what simplified like terms are and stuff?
Yeah.
Does everyone understand any mistake they made that they thought was or not? Yeah? Okay. Right, what are you going to do now? In the book, alright, we've got simplifying, we've kind of done all this. So practice 2, look. Alright, you've got which ones are like terms. I think we can probably go straight now to simplifying each expression. Now, there is one thing here. Write your answer in standard form. You might need to read the stuff before this exercise and figure out what standard form means. It's not that difficult. Alright? So you'll need the book. So get the book and it's page 149. And your book's out and you're going to do this exercise. So, this example here is 6x plus 5x squared minus, this one. Just, right. Can I ask you, guys, what is the difference between these ones? Can you use the correct vocabulary that we did in our first investigation? So the first one is A. This expression is a what?
Variable.
The expression has a term with a variable, and it also has a constant term h. But we classified that expression in our first investigation. What is it? Because it has a term with a variable, but it has a second term that is a constant term. It has two terms, so it is a... Go back to the first investigation.
Oh.
Begins with B.
Oh, binomial.
Binomial. It's a binomial. What degree?
One.
Why 1? Not because it's one expression, no. What was the degree of this? Nate knew this one. It's a binomial because there's two terms.
Because it's one, the expression equals.
Do you remember the degree being 1 is because the highest power is a 1. So this one is a what? So that's the degree is 2 and it is a trinomial. Now, you will notice it says here, be sure to write your answer in standard form. So these two answers are in standard form. Anything you can notice about what do you think standard form might
I'm
be?
guessing the first one ain't standard form, the second one is
No,
standard.
they're both standard form.
A standard form is just a proper.
What is proper? What is standard form?
Standard form is just the proper.
Let me give you an
Correct,
example,
right?
maybe on paper. All right. So 6x squared plus 5x minus 7. 5x minus 7 plus 6x squared. 9n plus 6. 6 plus 9n. What do you think?
I think for the first one, is it because in the equation, can you go back?
Oh,
to
the x's are paired up.
What?
Like the x's are together.
So
Not about pairing.
because all the n's, they equal, like it's 9 n's, so it's 9n, and then all the numbers in green are
Yeah.
added up to equal 72.
Well, that's the collecting the like terms. That's we've simplified, right? But why have they not written it 72 plus 9n?
Because it has the n and you have to get the n. You have to figure out what the n is to get your answer.
But I could happily write it the other way around. It's 72 and it's 9n's, yeah?
9n is
Standard form is just a standard way of writing it, Paige and Bondi, which states something. The standard way of writing it, which you don't always have to do, but the standard way of doing it is you take any term that has a variable comes before a constant. So the variable term gets written before the constant. But what if we have two different variable terms with different powers? Which one comes first? The one with the higher power. Simple as that. Alright? Do you remember the degree? So for instance, let me ask you this. 3p squared g cubed or 8p g to the power of 4. Which one would I write first?
8. 8 PD4.
Why?
Because it has
No.
a higher power.
No, it would be three PG.
Actually, in this case, remember you add those together, that's a 5. This is also a, it doesn't matter. But if I change this, okay, if I change this one to a g squared, this one now adds up to 3. So this one would be written first. Standard form literally says you add up the exponents for the term, and whichever one is highest, right? So that is a 5, that's only a 3. Whichever one becomes highest, that gets written first. And then the constant is always written at the end. Okay, so that's standard form. Maybe you need to make a note of that for next lesson. Okay?